Hello. So this will be my review of functions. And so you probably remember a function as y equals f of x. So it takes an x and as the input. Right? So x goes into the function. I'll call it f for function. And then y comes out. Right? Y is the output. Right? So all the numbers x that can go into the function is called the domain. Right? So it's just a collection of numbers. I'll use D for domain. Right? And then all the possible outputs gives you the range. Again, just a collection of numbers. So I'll call that R. Right? So for example, if the number 7 is your x, it might get mapped by the function f to the number 18. Right? The number -2 might get mapped to the number 48. Right? So we would just say f of 7 is 18 and f of -2 is 48. Right? So, yep, x is the corresponding input, and then the y's are the corresponding output. Right. And the important thing is that for every input, you can only have one output. So what cannot happen is if -2 is the input, we already know the output is 48. Right? It can't be 15. Right? It can't be both. It's one or the other. Right? So every input has only one output. So for each x in the domain D, right, there is only one value of f of x in the range R. Okay. And that's not to say that you might have two different x's going to the same y. Right? So for example, if x is 10, that might also go to 48. So f of 10 would be 48. So you can have the same y with more than one x. What you can't have is the same x with more than one y. So typically, we would think of functions as just equations, right? So if I write the equation y equals 3x plus 2, you can also think of that as a function, f of x equals 3x plus 2. Right? And so if I ask for, what is, oops, sorry about that. Yeah, so if I ask for f of 7, you would immediately know what to do. Just replace x with the number 7. So this is 21 plus 2 would be 23. All right. So now we're assuming, of course, that 7 is in the domain. Right? So the domain is not explicitly given, in which case we would just think of the domain as being as large as possible. Right? So the domain, right, unless explicitly given to you, which sometimes it is, but usually not, explicitly given, right? We're just going to assume is all real numbers, right? X, sorry, for which f of x is defined. Right? And by that I mean is also a real number. Okay. So for this function, f of x equals 3x plus 2, there's nothing that can go wrong here, right? The domain is naturally going to be all real numbers. Right? So you can use, right, this capital R, oops, for all real numbers, or in interval notation, it's just all real numbers from negative infinity to positive infinity. Right. And the range, so that's usually a little trickier to figure out because you have to figure out all possible outputs. But if the domain is all real numbers, right, then the range will also be all real numbers as well. Right. And if that's not obvious, just think of the graph, right? If I were to graph this function, and this is going to be a little sloppy, but I think you'll get the idea. This is just going to be a straight line with slope 3. Oops. Right. Passing through the point 0, 2. That's the y-intercept. Right. So yeah, it goes to the right and left forever, and it goes up and down forever. Right. And there's nothing missing. So that tells you that the range is all real numbers. Okay, so here's a trickier example. Right, so we have g of x is the function x plus 1 all over x squared minus 2x minus 3. And we want to find the domain. Okay, so how would we do that? So, right, in this case, we have to look at the denominator. If you remember, you can divide by any number except 0. Right, so we have to make sure that this denominator, right, does not equal 0. Right, so anything that makes the denominator 0 will not be in the domain. All right, so we're going to ask the reverse question. When is the denominator equal to 0? So to solve that, this is a quadratic equation. The easiest way to solve it is just to factor the denominator as x minus 3 times x plus 1. So either x minus 3 is 0 or x plus 1 is 0, in which case you get x equals 3 and x equals negative 1. So two values of x which solve this equation. And so there are two values of x which make the denominator equal to 0. Right? So these are the numbers that are not in the domain, which means everything else is. All other real numbers are in the domain. So what's the domain? It's the set of all real numbers x such that x does not equal either negative 1 or positive 3. Right? And in interval notation, well, if you think about a number line, right, here's negative 1, here's 3. What we want are all other numbers, right? So we have to skip over, oops, trying to make a hole here. We want to skip over negative 1 and positive 3. But everything else is in the domain. Okay. Right. So everything to the left of negative 1, between negative 1 and 3, and then bigger than 3. Right. So for interval notation, you're going from negative infinity to negative 1, and then union negative 1 to 3, and then union 3 to infinity. Okay. Right. So that's the interval notation. Again, it's just all real numbers that are not equal to negative 1 and 3. Right? We're skipping over negative 1, and we're skipping over 3. Okay. So also make sure you remember what happens when you have a square root. Right. Suppose we have f of x equals the square root of 6 minus 2x. We want to find the domain. Okay, so the main idea here is if I have any square root function, right, I can plug in any number, any positive number, and I can plug in 0. But if I try plugging in a negative number, hopefully you remember what that means. You get an imaginary number, and we don't want to deal with those, right? No imaginary numbers, you know, pretty much for the entire class, right? So anytime we get an imaginary number, we just cross it out, right? So the domain then should consist of all values of x that are either greater than or equal to 0. Right? Or in interval notation from 0 to infinity. Right. So that's for h. That's for just the square root function. Right? So we have something a little more complicated. What we have here is the square root of 6 minus 2x. Since that's under the square root, that is the thing that has to be greater than or equal to 0. Okay, so right, that's our x in this case, right? So x has to be greater than or equal to 0 if it's just the square root of x. In this case, it's the square root of 6 minus 2x, so that's what has to be greater than or equal to 0. So you solve that inequality, right? And hopefully you remember how to do that. You can subtract the 6 from both sides, and you can divide by -2. Of course, the problem with that is if you divide by -2, the inequality flips to less than or equals, right? So you get x is less than or equal to -6 divided by -2, which is +3. Right? So that's the domain. Right? It's the set of all x such that x is less than or equal to -3, or in interval notation, it's just from -infinity to 3. I'm sorry, +3. Did I say -3? Yeah. X is less than or equal to +3. So we're going from -infinity to +3. Right. And I'm using a square bracket to indicate that we include the 3. Right. In some cases, you just might want, say, x is less than 3. And in interval notation, that's from -infinity to 3, but with the parentheses indicating that we're not including 3. Okay? So, right, so that's the domain of this function, and you can check, just take any number less than or equal to 3, plug it in, and you'll see you get a real number. Right? So what happens if I try to plug in a number, say, bigger than 3? Well, bad things happen, right? So if I plug in 4, for example, it was the square root of 6 minus 2x. So 6 minus 2 times 2. 2 times 4, since x is 4. You just get the square root of -2, which is imaginary. And so we don't want to deal with it, right? So it's not a real number. We throw it out. So our mistake is we plugged in 4 when it's not in the domain. So whenever you try to plug in a number that's not in the domain, you end up in trouble, right? You essentially just get something that's either not a real number or not a number at all. For example, you might be dividing by 0, and that would be bad. Right? So just remember, you can never divide by 0. It's meaningless. Okay? Okay, one more type of example here. Suppose h of t is equal to 60 times t minus 10t squared. This represents the height of a ball thrown upwards with a speed of 60 feet per second from ground level, right, after t seconds. Okay, so we want to find the domain and range of this function. So the issue here, first of all, you should recognize that this is just a quadratic function. And right, the denominator is just 1, although we don't usually write it, right? Yeah. Right. So we're never going to be dividing by 0, no matter what t is. And there's no square roots, which means we're not going to get imaginary numbers. Okay, so you might think that the domain then would just be all real numbers. And so, yes, if given just this function without any context, without what it represents, then that would be a reasonable answer, right? T could be anything. But in this case, T represents time, right? And so you might want to draw a graph here. So if this is time and this is height, roughly what happens is you have the ball starting at ground level at time t equals 0. You throw it, it goes up, and it comes down. Right? So the graph will look something like this. Okay? So this, you might recognize this is just an upside down parabola, for example, right? So clearly, we're not concerned with what happened before we threw the ball, when t was negative, right? And we're not concerned with what happens after the ball lands. After all, once it lands, it's on the ground here, and that's it, right? So we can stop our clock at that point. So we're starting at t equals 0, and we're ending at some other time here. Obviously, that's part of the problem. We have to figure out what time does it land. Okay. But that's going to be, those are going to be our endpoints, right? T is going to be between 0 and then some other number, right? However many seconds it'll take for the ball to land, right? So how do we figure that out? Well, what happens when the ball is on the ground? When it's on the ground, its height is 0, right? So for what time, for what t, is the height equal to 0? So we essentially just have to solve this equation. And hopefully by now that should be pretty easy to solve, right? There's no constant term, right? So I can just factor out a t. In fact, I can factor out a -10 if you like. And in that case, we get -6 plus t equals 0. Oh, I forgot the t here, right? So t is either equal to 0 or t is equal to 6. Right, and these are in seconds, 0 seconds or 6 seconds. Right, so the 0 seconds we knew because that's when it started. And now we know that it's going to take 6 seconds to reach the ground again. Okay, so that's the domain. T is going to be between 0 and 6. All right. Now, they also ask for the range. So how do we find the range? Well, so the range are the y values, or in this case, y is the height, right, h. So the lowest point that this ball is going to be is on the ground, which is height 0. Right? So for the range, we know we're going to be at least equal to 0. And then how high do we get? Right? We get to the maximum height right about here. And so that's going to be our maximum height, right? That'll be the largest y value here. Right? So now how do we find that? Right, so that's a little trickier. But if you remember anything about parabolas, you remember that this point is the vertex. So you just have to find the vertex. And there's many ways of doing that. The quickest way, of course, is just to say, well, right, if it's 6 seconds to reach the ground, and this is completely symmetric here, that means the maximum height has to occur halfway in between 0 and 6, which is 3 seconds. So if that's the time at which it reaches the maximum height, oh, I'm sorry, we're using h instead of f here. So if I plug in 3 into the function, this is going to be 60 times 3 minus 10 times 3 squared. And that gives us 180 minus 90, which is 90, I guess we're in feet here. So 90 feet is the maximum height. Right? So that should give you the range. It's from 0 to 90. Okay, and yes, we're including 90 because it does reach the maximum height. We're including 0 and so forth. So that would be the corresponding range. Okay, so I hope that helps. And then let's do another example. This one's going to involve composition. Okay, so we're given two functions, f of x and g of x. And what can we do with two functions? Well, you know, you can add them, right? And you get a new function. We can just call f plus g. You can subtract them. Right? You can multiply them. And you can divide them. Right? So I'm assuming you know how to do all that. Right? Another thing you can do is compose them. Right? So that's f composed with g. This is the typical notation for composition of two functions. But it's usually much easier just to think of it as f of g of x. Okay? Notice that this is not the same thing as multiplying. Right? These are two different things. Right? Instead, composition is taking, well, it's taking a function, the two functions f and g, and just sort of chaining them together. So we think of x as the input of g first, right? X is going into the function g. And the output will, of course, be g of x. And then g of x goes into the function f. So the output of g now becomes the input of f. So the output will be f of g of x. And that's typically the way I'll write it, rather than write f with a circle g. But they do mean the same thing. So let's see how that works. Let's just start with an easy example. Okay, so let's start with f of x is the square root of x, and g of x is 3x plus 6. So we want to find first f of g of x. Right. I mean, I'll write it this way, but it's usually just f of g of x. Right. Well, there's a couple ways of thinking about this, right? I like to think of what does f do to its input, right? What does f do to x? Well, it just takes the square root of it, right? So what does it do to g of x? Well, it just takes the square root of g of x, right? And g of x is just 3x plus 6. So this is the square root of 3x plus 6. Right. What about going the other way? If we take g of f of x, right? So now what does g do to x? Well, it does two things. First, it multiplies it by 3, and then it adds 6. So what does it do to f of x? It multiplies it by 3, and then just adds 6. Right. So f of x is just the square root of x. So we get 3 times the square root of x, and then plus 6. Okay. So you can also, of course, compose a function with itself. You can take f composed with f. Right. So what's f of x? Well, remember, f takes the square root, so in this case it takes the square root of f of x. But f of x is already the square root, so it just takes the square root of the square root, which hopefully you remember is actually the fourth root of x now. Right? The square root of the square root is the fourth root. If you remember that the square root of x is, well, x to the power 1/2, by doing it again, you raise it to the power 1/2. And 1/2 times 1/2 is 1/4. And that means it's the fourth root of x. OK. What about g of x? I think if I have enough room here. G of x. So remember, g takes x, multiplies it by 3, and adds 6. So we're going to do that with g of x. We're going to take g of x, multiply it by 3, and then we add 6. But remember what g of x is. It's just 3x plus 6. So all I did was replace g of x with what it equals. Right? And we should probably multiply this out, right? 3 times 3x is 9x. 3 times 6 is 18. And then we have another 6 at the end. So 18 plus 6 is 24. So there you go. G of x is just the function 9x plus 24. Okay. So that's a typical example of composing two functions. Right. So now let's see if we can go the other way. Right? We have h of x is 4 over x cubed plus 2x plus 7. And now we want to take this somewhat complicated function and decompose it into two simpler functions, f and g. Okay, it turns out there's probably more than one way to do it, but I would think of this as simple as possible, right? So h of x is 4 divided by this rather complicated function, and so we might as well call that g of x, right? So the denominator here, the x cubed plus 2x plus 7, I'll just call that g of x, right? So let g of x be the denominator, x cubed plus 2x plus 7. Right. So what does f do to that? Well, right, it's just going to basically take 4 divided by what's inside. In this case, just x. So f of x then is just 4 divided by x. Okay, so let's see if that works, right? Let's compose the two functions as a way to check. Let's take f of g of x. So what does f do to x? It just flips it over, takes the reciprocal, and multiplies by 4, right? So 4 over x. But now we're taking 4 divided by g of x, and of course g of x is x cubed plus 2x plus 7. And we have the original function. That's our h of x, right? So this combination of f and g works. Okay? Like I said, there's probably more than one way to do it, but this, I think, this is the way that makes the most sense in my mind. And another thing we want to do with functions is find their difference quotient. Right? So the difference quotient of a function, I'll just call it f of x, is defined to be the following. Right? So it's going to be f of x plus h minus f of x all divided by h. This book tends to use h. In some cases, I use this symbol delta x instead of h. Right? So delta x and h are essentially the same thing. So in some cases, the difference quotient would be f of x plus delta x minus f of x all divided by delta x. So that's also the difference quotient. Okay, so let's start out with finding the difference quotient of the function f of x equals 5x squared minus 8x plus 3, and simplify. Right, so it's actually, the difference quotient isn't hard to find, it's the simplifying part. Usually involves a lot of algebra here. Okay, so, right, so this is our given function, and what we want to find is the difference quotient, which is f of x plus h, I guess I'll use h, minus f of x all divided by h. So what is that? So the first part, of course, is to find f of x plus h. Right? So everywhere I see an x, I just have to change that to what's inside the parentheses, namely x plus h. Okay, so f of x plus h is going to be 5 times, instead of x squared, it's now x plus h squared. Right, minus 8 times, again, instead of x, it's now x plus h, plus 3, right? So there's no x, so it's just plus 3. Okay, so that's going to be the first term of my numerator, if I can squeeze that in here. Squared minus, so 5 times x plus h squared minus 8 times x plus h plus 3, all divided by h. And don't forget, I still have to subtract the original function, f of x. Right. And I did something wrong, of course. This is a common mistake, right? You're subtracting the entire function. So I need parentheses around that. Okay, so just so we're clear, right, this part here is the f of x plus h minus, and then this part here is just the f of x, right, all divided by h. Okay, so that's the difference quotient. But notice it says simplify. And by simplify, we really mean just expand all this out as far as possible. Okay, so let's do that. It's just a lot of algebra. So first thing is, instead of multiplying by 5, right, we're going to have to multiply out x plus h squared, which is x plus h times x plus h. So you FOIL that, and you're just going to get x squared plus 2xh plus h squared. All right, and then minus, just distribute the 8, minus 8x minus 8h plus 3. And then we'll distribute the negative sign, so it's minus 5x squared minus a negative 8x, so that's plus 8x, and then minus a positive 3, all divided by h. Right, so we probably should have multiplied this by 5. Well, let's do it now. So this will be 5x squared plus 5 times 2xh, that's 10xh, plus 5h squared, and then just copy everything else down. Minus 8x, minus 8h, plus 3, minus 5x squared, plus 8x, minus 3. And then everything divided by h. Okay, so yeah, you get this big mess. However, it should simplify considerably. If you look at the numerator carefully, right, here we have a positive 5x squared. We have a negative 5x squared. When you add them up, you just get 0. Right? So they cancel. Right? And then you can do the same thing with this negative 8x and this positive 8x. That also adds up to 0. Right? And then finally, we have a positive 3 minus 3, and that's also 0. So most of the numerator ends up canceling. So what's left over now? Well, we have the 10xh plus 5h squared minus 8h, all divided by h. Okay, so there's two things we can do at this point. Notice that in the numerator, every term has an h in it. So I would factor out the h in the numerator, leaving you with 10x plus 5h minus 8, right? All times h, and then divided by h. Right? And by doing that, now notice that h divided by h is just 1. Right? And so we're left with 10x plus 5h minus 8. And that's as simple as it gets. Okay? Yep, if you're little bit fuzzy with the factoring parts. Here's another option. You could just take this fraction here and split it up into 3 separate fractions. Right? It's a little more work to do it that way, but it works, right? So you get 10xh divided by h plus 5h squared divided by h. Well, remember h squared is just h times h minus 8h divided by h, right? So I split it up as 3 separate fractions. Now, for each fraction, h divided by h is 1. So you can cancel the h in each term separately. And now what you get is, well, the same thing, 10x plus 5h minus 8. So either way, you get the same answer. Personally, I prefer just factoring out the h and just canceling it, but it works either way, right? The one thing you don't want to do is just cancel one of the h's, right? You don't want to say, well, this h and this h cancel. You can't do that because you haven't factored it out yet, right? You can't cancel terms. You can only cancel factors. So until you factor out the h here, you can't just cancel one of them. Right? For one thing, it gives you the wrong answer, right? It gives you 10x plus 5h squared minus 8h, right? Yeah. So if you're going to do it this way, and I wouldn't recommend it, you'd have to cancel all the h's in the numerator. But I would rather factor it out first. Okay. So that's right. This is something you've probably done before, so it's a good review, and we're going to do it again and again, for better or worse. And then maybe I'll do one slightly more difficult version of this. Okay, so we want to find and simplify the difference quotient for g of x, which is equal to the square root of x plus 2. Okay, so again, the difference quotient is g of x plus h, I'll stick with h, minus g of x, all divided by h. Okay. Well, what's g of x plus h? You just change the x to x plus h. Right? So it's the square root of, instead of x plus 2, it's now x plus h plus 2. Minus g of x. G of x is the square root of x plus 2, and then divide the whole thing by h. Okay, so that's the difference quotient. And at this point, you might say, well, it looks like we're done, right? It looks like there's not much else we can do here. But it does say to simplify. So how do we simplify something like this? So yeah, I just copied it down here. Yeah, so I'm just giving you a minute to think about this, because it's not easy. It does involve a little bit of a trick, and you might have seen it before, but maybe not. So right, so here's the trick. We're going to multiply numerator and denominator by the same thing. And that's going to be the square root of x plus h plus 2 plus the square root of x plus 2. Right? Instead of the minus sign, we're going to use a plus sign. In other words, we're going to take the conjugate of the numerator. The conjugate just means you switch the second sign from minus to plus. Okay, and again, to keep it the same, we have to multiply the denominator by the same thing. Right? And in that way, we're just multiplying the whole thing by 1, right? Right. Think of this as like 5 divided by 5. It's equal to 1. All right. So yeah, what we're going to end up doing here is rationalizing the numerator. Right? The denominator is just h times, well, the square root of x plus h plus 2 plus the square root of x plus 2, all in parentheses, right? And yes, I could distribute the h, but let's hold off on that. Instead, we're going to have to multiply out the numerator here, right? We're going to have to FOIL the numerator. So we multiply, right, the square root of x plus h plus 2 times itself. So when you multiply a square root times itself, right, you just square it. Right? And that gets rid of the square root. Right. Then you multiply the first times the last, so that's the outer terms. And that's going to be kind of a mess here, but it's going to be plus the square root of x plus h plus 2 times the square root of x plus 2. And then you multiply the inside terms here. So that's going to be a negative square root of x plus 2. Well, okay. X plus 2 times the square root of x plus h plus 2. And then finally, the last two terms. It's a negative times a positive, so it's going to be negative the square root of x plus 2 times itself. In other words, squared. Yeah, a big mess. But if you look carefully at these middle two terms here, you'll see that they're exactly the same. Just switch the order here. Right? 2 times 3, 3 times 2, same thing. So all this adds up to 0. It's just the same thing minus itself, right? 7 minus 7 is 0. Okay, so, right, and because we're squaring the square roots, the first term is just x plus h plus 2. And then the last term, because, right, all this is 0, is just x plus 2. And I'm just copying down the denominator, h times the square root of x plus h plus 2 plus the square root of x plus 2. Oops, 2. Okay. Right, and now we're almost done. If you look at the numerator carefully, we have x plus h plus 2 minus x minus 2, right? Don't forget to distribute the negative sign. And now a lot of things in the numerator end up canceling. Right? Hopefully you can see it. It's x minus x is 0, and 2 minus 2 is 0. So the only thing left in the numerator is just this h. And notice that there's a factor of h in the denominator. And so the two just cancel. Right, h divided by h is equal to 1. So the numerator is just 1. And the denominator is the square root of x plus h plus 2, and then plus the square root of x plus 2. And now we're done. So yeah, a lot of algebra. Again, I would encourage you to either look at it again or do a similar one. But in this case, we rationalize the numerator, right? Which sounds backwards, because up until now, you've probably rationalized the denominator a lot, right? If I have something like 1 over the square root of 3, we've always said that that's not acceptable. You can't have a square root in the denominator, right? And in this case, you don't need the conjugate. You just need to multiply numerator and denominator by, say, the square root of 3. Right? And by doing that, you get the square root of 3 over the square root of 9, or the square root of 3 over 3. So here we rationalize the denominator, but in some sense, we went backwards here and rationalized the numerator. And incidentally, at this stage, I no longer care if you rationalize the denominator, right? We'll get to the trigonometric function sine and cosine in a little bit, but in your trig class, right, you would write sine of 45 degrees, for example, as the square root of 2 over 2, instead of 1 over the square root of 2. Okay, so from now on, I don't care which way you write it, right? Either way is fine. Okay, so that's probably good enough for now for finding and simplifying the difference quotient. Again, the first one was a little bit easier because there was no trick to it. There's no rationalizing the denominator. It's all just multiplying and canceling. But when you see a square root like this, typically it'll involve some sort of rationalizing the numerator. So multiply numerator and denominator by the conjugate of the numerator. And after all this algebra, it should simplify. In this case, pretty simple, right? The numerator just becomes 1. So I hope that helps.